Hello, and welcome to the MECI 460 Design Conference. I'm Xavier Birdie from Group 16, BuzzBox Engineering, and we're here to present our Redesign Queen Bee shipping box. Before we get started, I'd like to introduce our team. So we are 6 final year mechanical engineering students at the university, and today you'll be hearing from Ahmed, Braden, David, Ryan, Shivanjali, and myself, Xavier. We'd like to talk about today is first run you through kind of an introduction, some background to our design problem, get to talking about our solution that we came up with, the analysis that went into that solution, and finally conclude by evaluating what we came up with. So I'll let Braden get us started with some of the background on the project.
Thanks, Zav. So in Alberta, there's 160 commercial beekeepers that require to have their queen bees imported from the United States. When queen bees are being transported, they must be kept within a viable temperature range of 15 to 38 degrees Celsius and must be able to be fed and cared for by the attendant bees. Once the queen bees arrive at the Canadian border, they must be inspected by the Canadian Food Inspection Agency to ensure they have no parasites riding along with them. In the market today, there are 2 existing products, the JZBZ products, as well as the California mini cages. The JZBZ products are used in international transport because they allow for easy inspection of the queen bees since they're completely separated from one another in individual cages. The California mini cages, however, use loose attendant bees. This is typically done in domestic transport and cannot be used for international shipping. I'm now going to pass this off to Ahmed to talk about the design objectives.
Thanks, Braden. The objective of this project was to design a queen bee shipping box that allowed attendant bees to remain loose within the box while still ensuring safe inspection. The box must have been able to withstand shipping conditions and be practical and easy to use. Some of the deliverables included a complete box design with engineering drawings and operating instructions. While designing the box, 5 key specifications were considered. These included ensuring an internal box temperature of 15 to 38 degrees Celsius with varying external temperatures, ensuring no bees can escape during the inspection process, a structural strength that enables 18 boxes to be stacked on top of one, a comfortable weight for users of less than 33 pounds, and an overall cost of less than $1.50 per queen bee. Some additional factors that were considered while designing the box included trying to develop a single-use, environmentally friendly box. A reusable box was deemed not feasible because beekeepers are usually located in remote areas and it would be a hassle to ship back and forth. We also researched how much heat bees can generate as well as how much heat loss they can induce. Research was also conducted to determine how bees interact with each other to ensure maximum viability upon arrival. Lastly, we designed a box that is easy to use for beekeepers and inspectors and something that is actually practical enough to be put in practice. Now I'll pass it on to Shivanjali to discuss the concept selection.
On this slide, we will now go over our 3 defined concepts. The box-in-box concept uses existing JZBZ queen cages arranged on shipping bars, which are placed in the queen transportation box. The attendant box contains loose attendants, is designed with a flexible mesh on its base that wraps around the queen cages upon assembly. This allows for attendants to surround the queen cages and feed the queens. The queens can be inspected either through the mesh windows on the sides of the queen box, or for a closer look, the attendant box can be pulled out, which allows full access to queen cages inside the box. The cage and slot concept uses existing 3-hole queen cages that simply line up over a separator, and the cages are held in place with a foam support. The outer wooden frame has loose attendants in the bottom portion, which can access the queens through the slotted separator, and a top mesh allows the queens to be inspected at the border without pulling the cages out. Finally, a lid goes over it to complete the assembly. The tube and cube concept, as the name suggests, contains individual queen cages threaded together into tube assemblies, which are integrated into a main box. The tube assembly with cages can be pulled out for inspection, and is designed with a bottom stopper that threads into the top lid so that the loose attendants in the main cube cannot escape. When the tube assembly is slid back in, the top cap threads into the lid such that the bottom stopper does not go all the way in and injure any bee underneath. The base of the cube is covered in mesh and allows for inspecting loose attendants. Moving on to the next slide, we look at some of the differentiating decision matrix parameters that allowed for our concept selection. The first criteria is attendant thermoregulation, which refers to attendants clustering around the queens to keep them at a comfortable temperature. The box-in-box design allows attendants to access about 89% of the queen cage surface, as it has mesh that wraps around queen cages. The tube and cube concept is a close competitor at 80%. The next criteria, which is inspection, refers to how much of the interior volume is visible from a single inspection point. The box-in-box again has the highest visible volume at 55%. Now looking at the material strength, we can see that cage and slot and tube made of Wood and plastic are stronger than the cardboard design. However, the cardboard significantly brings down the weight of the box-in-box to approximately 10 pounds and results in a lower cost per queen. These parameters significantly impact the scoring and favor the box-in-box concept. Now, I hand over to Xavier, who will go over a design overview of our selected concept.
Thank you, Shivanjali. So our design, the BuzzBox, is meant to mimic domestic transportation by having attendant bees who are loose surround the queen. Now on the right, you can see how the box comes together, with attendants in the inner box contained by the wrapping mesh, and queens in the cages. Now, although the attendants are enclosed, they can access the queen through the mesh cage interface. This interface is maintained by the support rods, which hold the mesh against the cages. So the first component to look at is the outer box. The outer box houses all of the queens in their queen cages and provides the general structure for the box. It also has the ventilation holes, which allow proper gas transfer that the bees need in order to survive. Now, all of the cardboard components for this design were designed to fold from a single flat pattern in minimal steps. And those are the animations that you see right now and that you'll see on some of the subsequent slides. The next component to look at is the inner box. So the inner box houses all of the attendant bees and allows them to be loaded before being shipped. As you can see from the section view, the wrap mesh winds its way around the support rods so that there are gaps created so the queen cages can be inserted before shipping. Again, we have folding pattern on the right. Some of the other components to consider are the lid, which obviously encloses the whole space and distributes the load onto the rest of the box. The JZBZ cages, which are an industry standard for the beekeeping industry. And then finally, the bar support, which is meant to hold the cages at the right location during transportation. Now that you have an idea how the design sort of works, I'll pass it on to Braden for the analysis.
Thanks, Zab. We had three main components of analysis that we performed on our project. First off, Shivanjali and Ahmed will talk about the thermal analysis. David and Ryan will chat about the structural analysis. And I'll return at the end to talk about the cost analysis. So first off, Shivanjali and Ahmed.
The main objective of a thermal analysis is to determine a ventilation window size, which allows bees to maintain a comfortable internal temperature while ensuring a safe concentration of respiratory gases within the box. The prime assumptions include that the flow is buoyancy driven, the attendants are uniformly distributed within inner box, and they can generate a constant amount of metabolic heat for external temperatures below 26 degrees Celsius. The evaporative heat loss value by the bees and the discharge coefficient were obtained from previous experiments, and the model only looks at a steady state solution. The bees perform several thermoregulation activities, and in case one, we see that when external temperature is dropping below 26 degrees Celsius and it's getting colder for the bees. In that case, the attendant bees warm up the queens by producing a metabolic heat of about 0.049 watts per bee. And since we have 4,368 attendants inside the box, they can produce an overall heat of 205 watts. In case two, when the external temperature is rising above 30 degrees Celsius and it's getting hotter for the bees inside, the bees drive out hot air by coordinated fanning activity, producing a combined velocity of 2.24 meters per second. This fanning response is also triggered due to the rising carbon dioxide inside the box. Another way to cool down the box is evaporating cooling that the bees undertake, producing a heat loss of about 0.086 watt per bee. On the next slide, we're going to look at the equations that are built up based on this model. So here we look at the heat balance equations where case one refers to when the external temperature is dropping below 26 degrees Celsius and it's getting colder for the bees inside the box. So the first term on the left-hand side refers to the heat loss due to warm air flowing out of the box. Another term for heat loss is due to internal warm air conduction at the box surface. The only source of heat generation in this scenario is the metabolic heat generated by the bee muscular activity. In both the equations that we're going to discuss, pressure is a function of temperature. Now in case two, when the external temperature is increasing beyond 30 degrees Celsius, the bees take up evaporative heat loss to dissipate some of the heat inside the box and cool it down. On the right-hand side, we look at the source of heat generation is the warm air flowing into the box due to buoyancy, as well as the bees fanning fresh air into the box. Another source of heat rise is the external warm air conduction at the box surface. Now, in case one, we talked about the metabolic heat generated by the bees, which is evaluated using an exothermic oxidation reaction. which occurs when the bees consume candy that's provided to them not only as a food, but also to help them with the thermoregulation activities. The metabolic heat is determined from an experimental value of volume rate of oxygen consumption, which is about 131.4 microliter per minute. And in the next slide, Ahmed is going to go over the results of this model.
So using the equations mentioned in the last slide, we wanted to determine the relationship between three key parameters: the outside temperature, the inside temperature, and the area of the window which allowed for ventilation. By determining this relationship, we could validate an appropriate area of the window. This surface plot on the left represents this relationship. From this surface plot, we learned that a large area of the window yields in a greater range of interior temperatures, which makes sense. If the ventilation hole was small, less heat would enter or exit depending on the outside conditions. Again, an interior range of 15 to 38 degrees Celsius is what we wish for. This is represented by the two bounds shown on the left, the upper limit and the lower limit. After studying these results, we decided to pursue a window area of 8 inches squared. Although our calculations indicate that a small area of a window is ideal, we wanted to select the largest area possible while still ensuring the comfortable range of temperatures for bees. This was because we wanted to account for any potential mishaps while shipping. If for some reason the windows get accidentally covered during shipment, a larger window size yields in a higher chance of appropriate ventilation to still occur. The other thing we checked for was to make sure that the CO2 generated by the bees was being flushed out appropriately based on the window size. We used the exothermic oxidization reaction again for this by assuming the exterior temperatures and the interior temperatures were equal, and that the only driving force of flow was caused by the bees flapping their wings. It gave us the highest possible value for the CO2 generated in the box. The stoichiometric calculation provided us with the minimum area of 0.04 inches squared to meet the CO2 discharge requirements. Since our selected 8 inches squared is much larger than this, we can conclude that the area is sufficient for CO2 clearance. I'll pass it on to David now to discuss this structural analysis.
Thanks, Ahmed. The structural integrity of the box was verified to ensure it was safe to use. I'll be talking about the analytical calculations while Ryan will discuss the simulation results. The purpose of the analytical calculations are to ballpark the FEA results to improve validity. Cardboard isn't normally simulated because with cardboard's corrugation, the simulation becomes extremely complex. The only way to do a proper failure analysis must be done through experimental testing. However, due to time constraints and budget constraints, we are unable to test cardboard boxes to verify structural integrity. Instead, we've used a multitude of research papers to create some simplifications and assumptions, including a comparable Young's modulus. For this design, the cardboard is assumed to remain in a dry state throughout transportation. Additionally, it is assumed that boxes with smaller holes in the wall and are shorter are actually stronger, meaning if we do a direct comparison, our box will be over-designed. This means that through a comparison to existing boxes using a stress comparison, with the experimental box being able to handle 1,591 newtons, our box is able to handle the expected force of 805 newtons as the allowable estimated force is 1,135 newtons. And now over to Ryan.
Thank you, David. This is our FEA results. As you can see, the deformation plot closely resembles a buckling problem, and the load is applied right at the top lid, so the results make sense. On the right, we have the enlarged image for the deformation, which happens in the inside wall. As we can see that the deformation happens horizontally, which makes sense, again, because of the buckling. The factor of safety plot shows that most regions have FOS of greater than 10, and the minimum factor of safety occurs at the bottom edges and at the cutouts. On the right, we have the enlarged view of the minimum factor of safety, which is affected by the mesh quality. And from this case, our mesh is perfectly fine. On the right, we have the two mesh dependency plots, one for minimum factor of safety and one for maximum displacement. As you can see that both parameters are converging as the number of nodes increases. The main purpose of this finite element was to determine if the current box dimensions are enough to hold 18 boxes. And as you can see, our factor of safety is greater than 1, which is great. The stress that was used was determined from a paper that had the minimum compression strength. So again, this is supposed to represent a conservative approach to determine if the box would fail or not. And now I'll pass it down to Braden.
Thanks, Ryan. I'm now going to chat about our cost analysis. So in order to determine the overall cost of the box, we looked at using unitized costs from manufacturers and then prorating those rates across our design. In order to reduce the cost per box, we looked at the overall manufacturing quantity of 27,000 boxes per year. This would satisfy the import requirements of queen bees from international destinations. When determining the labor costs, we looked at using a time step approach and an unskilled worker rate at 65% overhead to determine the overall cost of labor. So looking at each individual component, we see that the outer box, inner box, and lid combined together cost about a total of $30. That includes things such as the cardboard, the mesh, and the support rods. Adding in the JZBZ cages, bar supports, and other shipping items to get the box ready to be shipped, that adds an additional $52.09. And then finally adding in that assembly labor of $8.84 gets us a total cost per box of $90.51. That relates to an overall cost of $1.08 per queen bee when it comes to the shipping costs. Now I'm going to pass this over to David to chat about the design compliance matrix.
Thanks, Braden. We ensure design compliance across 5 key areas, these being temperature, inspectability, shipping, weight, and cost. We comply with every single aspect of the specifications laid out by the client and existing standards. Now, these compliances are making sure that the queens are kept between 15 to 38 degrees Celsius for temperatures between 12 degrees to 42 degrees Celsius. This is within the range of our specifications. The other aspect is attendants must be visible but enclosed, while queens must be in removable cages. This is also within our specification of making sure they don't escape. Our factor of safety of the box is 1.69 at 805 newtons, which is the withstandable stacking of 18 high boxes, and that is the weight, giving us the 805 newtons. Each box weighs 19.5 pounds, which is less than the allowable weight. And last but not least, the box costs $1.08 per queen, which is less than the specified client request of $1.50 per queen. And now back to Braden.
Thanks, David. There are 4 categories of future work for the project. On the thermal side, completing a transient analysis and a CFD simulation will help us further verify the internal temperature profiles of the design. On the structural side, completing a prototype and crush testing it would help verify our FEA and our analytic solutions. On the cost side, engaging with lower cost suppliers to further decrease the cost of the box. And from the usability side, engaging with the CFIA or the Canadian Food Inspection Agency to seek approval of the new design. I'm going to pass it to Zav for some closing remarks on the presentation.
Thanks, Braden. So to close us off, I would just like to thank Dr. Flynn and Dr. Nakashima from the University of Alberta for their help on the project, as well as our client, the Alberta Beekeepers Commission, and Dr. Shelley Hoover from the University of Lethbridge for her help on the project. And finally, thank you for listening. We hope you enjoyed our presentation. If you have any questions, feel free to reach out and enjoy the rest of the conference. Thanks.